Okay, so I'm Wim Thielemans, and we're going to go a little bit more back to the basics, looking at surface interaction and assembly of nanocellulose, because we find that a lot of issues that are found in processing and making materials actually are due to basic fundamentals and small differences between different samples. So Gilberto and Peter already introduced nanocellulose, so I don't have to go, I saved myself a slide. But one important thing is if we look at the crystalline structure of cellulose, so we know that we have the cellulobiose unit, and I'll have to start this, yeah. And then you have the cellulose chain where everything is flipped, so you have a primary hydroxyl to secondary hydroxyl groups. These cellulose chains are then stacked into a crystal where on the outside you see planes where you have a lot of hydroxyl groups that stick outside in the equatorial positions. And all these chains are very nicely aligned. In between the planes, you have van der Waals interactions. They're individually very weak interactions. So here you only have van der Waals interactions. They're individually very weak, but because you have them along very long chains, they become very strong altogether. So here you have all the OHs sticking outside in the equatorial position. And here on in these planes, you basically just have hydrogens, and there you have very weak interactions. Now there is a lot of controversy on what the exact crystal structure or the individual monocrystal is. So these are two other models that are currently being discussed, and it's a very hot debate in the cellulose community, as hot as it can get. But what is very important is that in these two crystal structures, you see here on these parts still the very hydrophilic faces where you have all the hydroxyl groups, but you also have very hydrophobic surfaces on this side where you don't really have any polar interactions. So that makes that these cellulose nanocrystals are actually amphiphilic and can behave very hydrophilically on these sides and very hydrophobically on those sides. And those are actually very important aspects. Now, if you look at cellulose nanocrystals, we know that if you increase their concentration in aqueous suspension, if you have stable suspensions when they're sterically stabilized, so these are, for example, with sulfuric acid hydrolyzed, as you increase their concentration, they go from isotropic, where the particles can, in theory, move freely in 3 dimensions. And at some point, some of the particles will start aligning, and they form chiral nematic phases. And as the concentration goes up, basically your isotropic phase reduces, your chiral nematic phase increases, up until you have a concentration where everything is chiral nematic. We know that, that's very robust. If you make these nanocrystals from different sources, if you wait long enough, if you do your extraction properly and your purification properly, this will always happen. We know that if we can dry them, we can create color, structured color, because you can align, you can keep the alignment of the particles on the surface. It starts refracting light, and you can generate color actually without using any colorants, purely because of the diffraction, the preferential diffraction of light. You can do it via droplet drying, you can do it via film casting. You can make 3D structures via hydrogen bonding interactions and then dry it and aerogels. And these are things that we can always do, and it's very robust and it's very reliable to do it. So what are the issues? Well, while it's very robust, there's still a lot of fundamental questions that remain because we can't really control the interactions because we don't understand them fully. And that is something we still need to work on. We don't have full understanding of what dimensional variations in the CNC sizes is and of their surface functionality on their assembly behavior. The transition between the isotropic and the cholesteric or chiral nematic phase, so that between the completely free moving particles and the ones that are aligned in solution with increasing concentration, is also not very known. We tend to have to wait a couple weeks, sometimes months, for these assemblies to happen. I'm a chemical engineer, I want things to go fast. So if we ever want to produce these at a large scale, these structuring, we need to understand the kinetics so we can do it much faster. And then if we can sort this, we can do some, make some materials with added reliability. So let's go to some of the things that we've been working on. If you look at the interactions, then we'll see that all interactions are based on polarity differences. Always something positive with something negative, something delta positive to something delta negative. Water can undergo all these interactions. So that means that all interactions are inherently hydrophilic. Hydrophobic interactions do not exist. Right? Everything is based on differences in polarity. That's first year chemical engineering. Now, why do you then get apolar particles going into an apolar solvent? Well, we know if it's a spontaneous process, and that is a spontaneous process, the Gibbs free energy has to be less than 0, you have an enthalpy, and you have an entropy term. So, if you say maximum enthalpy, then your apolar particle should be in water, because in water it can undergo more interactions. Your apolar particle will be more polarized in water, so will have more interactions. So, if we base it on enthalpy, all our particles should be in the water, or all our hydrophobic molecules should be in the water. If you look at pure entropy, we want maximum amount of chaos, maximum amount of distribution. We want as many particles in our hydrophobic solvent and as we have in the water solvent. So we want maximum distribution. But actually what we see is that all the particles go in the hydrophobic species. So why do we actually get this? The reason is not because the hydrophobic particle wants to be in the hydrophobic solvent. It's simply because if we have a nonpolar solute in water, the water molecules will structure around it. And so all these water molecules will lose degrees of freedom, and they don't like it. So what they will do is they will push your hydrophobic molecule out of the water. At that point, when you get the phase separation or your hydrophobic molecule goes in the hydrophobic solvent, these water molecules will regain their freedom and they increase in entropy. So the hydrophobic effect is a pure entropy effect and is not because of interactions. Right? And that's very important. So can we see this on the cellulose? Yes. If we do simulation, so we look at cross sections, and this is for nanofibers, we can actually then fill our volume with water molecules. We can let it equilibrate and see how the water molecules structure around our cross section. And what we see that along the hydrophilic planes, if we look at the interactions there, we have more polar interactions, so we have a higher enthalpy of interactions, but we have a much lower packing, so much less water molecules on these phases. If you look at the hydrophobic planes, we see that the water molecules are packed in a much more structured way, so they have a very large reduction in entropy, but there's very little actual polar interaction. So if we then take an apolar drug molecule, for example, and we also modulate or we calculate how the water molecule structure around it, we can see how these will interact. And we see that these hydrophobic molecules will preferentially go to the hydrophobic faces of the cellulose. Not because it likes the hydrophobic faces of the cellulose, but at the point that they interact, the water molecules that would normally be in between here are released, regain their freedom, and so it's purely entropy based. Yeah. So that means these are non-specific interactions based on entropy gain. We get from calculations that the Gibbs free energy of these interactions is somewhere around 25 kilojoules per mole. That's a number that will come back a little bit later. So that means that if we extract nanocellulose, that we actually, if we do get hydrophobic species in our extraction solvent, they will absorb onto the cellulose, because it's basically, again, entropy effect. So if you take nanocrystals and we look at the actual carbon content, this is the carbon content you would expect for pure cellulose, then you see that we actually are nanocrystals which have been purified, are not pure cellulose. If you start successfully extracting them with different solvents, and we did a whole bunch of different solvents than these, then you see that you increase it, so you start extracting species which are not cellulose, and you get closer. Ethanol is the best one we found. You don't get perfect. We'll come to that. And if you start determining then what are the things you extract, well, you get all these molecules that you get from sulfuric acid, breakdown of cellulose, and you get some of these aromatics, which are dehydration products of cellulose as well, that you can form. So basically these are things that you get from your acid hydrolysis. So if you want to do surface modification, you have to do oxide extractions to purify surfaces. Yeah, it actually makes sense once you know it, but like 10 years ago, nobody purified their surfaces before trying to modify. Now, where does this difference come from? Well, we also know that cellulose is hygroscopic. It's a high energy surface. And if you do the calculation, the surface energy of cellulose with air is higher than the surface energy of water with air plus the surface energy of water with the cellulose, the interfacial energy. So that means that if water absorbs on the cellulose surface, the total system will have a lower energy than the cellulose in a dry state. And we actually can determine that. So you take nanocellulose, you freeze dry it, you put it immediately in the TGA. You see that you have around 4 or 5% of water on the surface that you evaporate before you get to 120 degrees. And you can also calculate that from elemental analysis. So if you correct your elemental analysis for the water content, you actually get to almost pure cellulose of your data. The exact amount will depend on relative humidity, pressure, temperature. So anytime we do elemental analysis of nanocellulose, either pure or modified, we run a TGA in the same lab at the same time to basically be able to correct for the moisture content. It's also important to remember then that if you start modifying cellulose or working with cellulose, there's a very high likelihood that there is a small layer of water on the surface, even if you try to purify it. Then if we we wanted to look more in more detail to the surface interaction. So we did isothermal titration calorimetry, where you can, with every injection, you basically measure the heat of interaction of whatever you inject with the nanocellulose surface. And every injection gives you a heat trace. Then if you plot that from the height difference here, you can get the enthalpy of interaction. Then from the inflection point, you can get the equilibrium constant. The equilibrium constant allows you to calculate the Gibbs free energy. And from the first law of thermodynamics, you can calculate the entropy of interaction. So you can get all the thermodynamic parameters. And we did a whole bunch of experiments with salts, proteins, polymers, hemicelluloses. And we also did a review of the literature. And if you plot the enthalpy of interaction versus the entropy interaction, you find that all data points fall about on a slope, on a straight line. This straight line, if you take the slope of it, it's around 25 degrees. It's 298 Kelvin. And most of these measurements were taken at 25 degrees, so it matches up. The intercept is minus 23 kilojoules per mole, and you take this equation, you actually see that the intercept is the Gibbs free energy. So interactions at the surface of the nanocelluloses have an almost constant Gibbs free energy, which means that whatever you interact, you can't really make the interaction stronger. You can make the interactions more specific by playing on enthalpy, but as soon as you play on enthalpy, you lose on entropy, because you have what we call an entropy compensation mechanism with almost a constant Gibbs free energy. And that's a system that's very common. You see that a lot with amphiphilic surfaces, where you get that compensation mechanism. This goes over the whole range, where you get here individual ions, all the way down to proteins with cellulose binding domains, right? Over that whole range. So it's quite consistent. We can also use that to look at gelation of CNCs or CNFs with, for example, this is an example with divalent cations, where you have CNCs with sulfate groups in the acid form, or CNCs with sulfate groups in the sodium form, so neutralized. If you do the injections, at one point you'll see that your baseline shoots up, and that's when basically because the stirring, because you have a stir in your system, generates enough heat. The reason for that is because you get gelation, so you can get very detailed information on the critical aggregation concentration as you add your divalent cations. If you do these measurements, your Gibbs free energy is again roughly around the 23 kilojoules per mole. So the absorption of divalent cations on charged groups of an opposite charge is again entropy driven. Quite surprising when you bring two things together. Very interesting, you can also get the concentration that you need. With sulfates, it's a 1:2 concentration, and that's almost a 1:1, right? Like two calciums can bind, well, one calcium can bind with two sulfate groups. With carboxylates, it's only a 1:10, because as you bring carboxylates groups close enough together, even when they're both negatively charged, can bond with each other. So you don't have to have a 1:1 ratio. We find the same for calcium. We find the same for magnesium, strontium, and barium, that these ratios stay roughly the same. When does it change? If you take cellulose nanocrystals and you put two functionalities on it, you put sulfates on it, and you put carboxylate at the same time, then you find that your ratios change with the size of the ion or the hydration state of your ion. This is something that baffled us for a while. Why would it change if you have these double functionalities? It's again an entropy effect, where the surface of structuring of the water is less homogeneous when you get two functionalities on the CNCs, but it actually allows you to control how much salt you have to add, and very interesting, you can also control the gel strength that way. So with multiple functionalities, you have more control over the strength of your gel and how your system actually gels. So maybe we shouldn't we should stop making monofunctional materials and more start thinking about adding multiple functionalities, because it'll give us more control. Of course, it'll make it more difficult, but we'll figure it out and gives us a little bit more work. Then if you look at dimensional variations, let me check for time. Oh, no. Cool. If you look at dimensional variations, so we made two batches of CNCs from different sources. We tried to get dimensions roughly the same. But what you see is if you take them from cotton or from wood at 3.5 weight%, 5.5 weight%, you see that the amount of the chiral pneumatic phase in both is very, very different for these relatively small differences. If you look at the average length, the aspect ratios, the surface charge is roughly the same. So for these small differences between these two, you get very different or very large differences. This is the amount of chiral pneumatic phase relative to the complete volume. So for these small variations, you get very large effects on macroscopically. But also, if you look more detailed, if you look at the diffusion coefficients of these CNCs, so this is the rotational diffusion coefficient, which we can measure via light scattering. This is the diffusion coefficient, the translational one in the length of the CNCs. This is the translational one perpendicular to the length axis of the CNCs. You see that these particles, even though their length is relatively similar, the effect on the rotational coefficients and the translation diffusion coefficients is very, very large. So even small effects, small differences in the average dimensions of the particles can have a very large effect at how they behave. And we also noticed that even though we make batches from the same CNCs with small differences, the time it takes for them to actually self-assembly can be very different. Sometimes you have to wait 1 week, sometimes you have to wait 2 or 3 weeks. And that's because of these large effects that you can have. If you look at the transition between the isotropic and the chiral pneumatic or cholesteric effects and the kinetics of self-assembly, because they're kind of related, then we made 5 suspensions, which up to 5 weight% were still isotropic. When you shake them under cross polarizers, they start giving you color. The reason that even if they're isotropic here, isotropic and concentrated isotropic, once you start shearing, you start aligning them, and you basically have shear-induced alignment of your nanocrystals. So at rest, they're completely black. They're not. They don't show you any polarization. But if you put them in, this is neutron scattering. If you put them in neutron scattering, the isotropic phase, you see this is a structure factor. You see a structure factor, so it actually shows that your CNCs are already aligned in your isotropic phase. It looks macroscopically isotropic, but your nanocrystals are aligned. So it's somewhere here where in the isotropic phase you have aligned domains, or we should have aligned domains. Very interesting here. If you measure the dimension here, it's the separation between the CNCs is about 80 nanometers, while the biolength is only around 4 nanometers. So the separation distance between the CNCs is an order of magnitude larger than the biolength. So this alignment is not purely driven by electrostatic repulsion. We believe it's entropy driven, and we have proof for that. If you measure the diffusion coefficients, you actually see that at a point where you do get where you get more alignment, you see that your translational diffusion coefficient goes up. The only way you can get an increase in translational diffusion coefficient is if your particles start aligning. But if you have phase-separated systems, where you have an isotropic and a chiral nematic phase, then you will actually see, if you take SANS measurements of the chiral nematic, the light ones is the chiral nematic, the dark one is the isotropic. So the chiral nematic and the isotropic, you see that you have here structuring, this peak that you see here, falls roughly at the same time. So it seems like the separation distance between your particles in aligned domains that float around in your isotropic phase is the same separation distance in your chiral nematic phase at the bottom. That's again a sign that it's an entropy-driven process. We can also get this assembly in drying drops, but we all know if you dry a droplet, particles will go to the sides and accumulate there, and the effect is that you get the so-called coffee ring effect. If you dry your CNCs slow enough, what you get is you get these lines here that are colored on the outside because of changes in thickness. And in the center, you get aligned CNCs, and there you get the structural color formation. As you increase your concentration, basically your coffee ring effect gets more pronounced, and you get higher sides. So what we wanted to do is, can we avoid this coffee ring effect? And for that, you can use Marangoni flow. So you play around with surface tension gradients on the surface of your particles. You can play around with it by doing the drying in an atmosphere with organic product, which will diffuse in the water. And if you, I'm a chemical engineer, so I like dimensionless numbers. So you can start calculating the differences between the magnitude of capillary flow and Marangoni flow relative to the evaporation velocity. I'll spare you the mathematics. If you do it under pure ethanol vapor, you can get a very nice homogeneous deposit, but you don't get any color. Why? The ethanol will too fast go into the water, and it will destabilize your colloidal system, and you don't get nice alignment of your CNCs. So you still need water. If you take 50-50 ethanol methanol water mixture, then your Peclet number is more correct, and you still get a relatively nice homogeneous deposit, and you get also alignment of the CNC, so you get much better structuring. Now, of course, every different color is a slightly different aligned grain of CNCs. So the trick is now to actually see, can we get a long range order over a long time? And I have still a couple minutes. So some examples of where we apply some of the knowledge that we have in materials. One is co-assembly with conducting polymers. So we have CNCs which are negatively charged. We have them in an aqueous suspension with pyrrole, and we have an electrode. We apply a voltage. The pyrrole is electropolymerized to polypyrrole, becomes positively charged. it sticks to the negatively charged CNCs, and you basically get a porous deposit of CNCs coated with polypyrrole. We can, if you normally deposit polypyrrole on an electrode, you get kind of a mess on your electrode. With the CNCs, it grows very nicely as a cylinder from your electrode upwards. Yeah. Again, the deposits with the CNCs is nicely porous, whereas this deposit of polypyrrole by itself is more scattered. We use these as electrodes for supercapacitor materials. They give you about 10 to 30% higher capacitance of this relative to the pyrrole, which is not really something to get too excited about. The nice thing is you get a coating of about 6 nanometers on top of the of polypyrrole on top of the CNCs. And during your cycling, it has an important effect. So this is a voltammogram where we basically cycle our voltage, and the volume or the area in between this graph is a measure for the amount of charge you can store. This is the polypyrrole electrode at the beginning. This is the polypyrrole after 1,000 times cycling. So 1,000 times cycling is charging your phone for 3 years every day, which is kind of a standard that people use. Just the polypyrrole loses about 50% of its storage capacity. With the cellulose, because it's such a thin layer of polypyrrole on the top, you get a lot less mechanical disintegration during cycling. You lose about 3%. At the moment, we have electrodes which actually don't lose any storage capacity over about 5,000 cycles. We can actually make thicker electrodes, so you can create relatively thick electrodes, which still have the same properties, which is something you cannot really do with metal oxides. If your electrode gets too thick, it doesn't work anymore. And then if you make your supercapacitor, you get close to 10 watt-hours per kilogram, which is kind of where you need to get to become interesting commercially. And then with these, we did a test of 50,000 cycles, which is a bit ridiculous. And nobody has a mobile phone for 150 years, but it might be interesting in a car for recovering energy when you brake. And there you still have almost half of your capacity. So now we're looking at the effect of surface functionalities of CNCs and supporting electrode during electrode deposition to actually boost these values a bit more. And then finally, we're using these CNCs also to flocculate microalgae. Microalgae are cells which are negatively charged. They're very stable. The problem is they grow at low concentrations. They're relatively small and they're negatively charged. So they're very hard to harvest. One way to get them is via flocculation. The biggest problem is if you add positively charged polymer, if you overdose, you actually restabilize your suspension again. The second thing is that the most interesting microalgae from a sustainability point of view are grown in marine water, in marine environments, so in salt water, because we have a lot more salt water. And most flocculants don't work in high ionic strength because they coil. We have a benefit. We have CNCs. They're rigid. They cannot coil. So we made CNCs with positively charged groups, pyridinium and imidazolium groups, and we can control the degree of substitution by temperature, reaction time, and the reagent concentration. Yeah. And so with sweetwater algae, we see that we get very nice flocculation, 100% with the modified CNCs, and we don't get restabilization. The reason for that is the mechanism, and I'll spare you the details, but we actually proved that it's via a patch mechanism, so you can never get restabilization that way, and the efficiency of flocculation scales with the amount of surface groups you have on the surface. Very interesting is that this also works with marine algae. So this is the RCNCs, and chitosan is also a polymer being used to flocculate. But here, so these are algae. We added the CNCs or chitosan. Well, you'll see, I don't know how long this goes. I'll see if I can speed this one up a little bit. If I can find where my... Yeah, I can't find where the cursor is. What you'll see is right before, after the movie ends, when you stop stirring, you'll actually see all the microalgae nicely dropping to the bottom here and staying in suspension there. So we're almost there. How to get a room quiet. Yeah, and then they stop, and you see a lot stay in suspension here, whereas there, the water actually clears very quickly, and you get nice flocculation. These flocks, you can also filter them, and you get to, with a relatively large filter at 20 to 30 microns, which doesn't give you too much of a pressure drop, and you get almost 100% recovery of your marine algae. So finally, the CNC chemistry is relatively well understood. We know what these surfaces look like, what we can do with them. We need some serious in-depth knowledge on thermodynamics and the kinetics of cell assembly, and we're sorting through a lot of these things. The assembling systems can give significant variations with very small differences in the starting material, so initial characterization of material is critical. We're getting some better characterization techniques that allow us to see things that before we couldn't, and sometimes we have to completely rethink how we looked at these materials, but that's good. We can make some materials with characteristics that we cannot get from non-renewable materials. We just have to use the special properties that these materials have. So finally, I thank the research group and people we've worked with, funding agencies, and Samuele for organizing this workshop. Yes, thank you very much.